Hello, my name is Bon Sheedy, and welcome to my presentation on Nanoimprint lithography, or NIL. We briefly covered nanoimprint technology during our second week of lectures, and I'd like today to delve deeper into the intricacies as well as its interesting applications. But first, let me make a quick note on alternative lithographies and why nanoimprint is an important area of research. There are other technologies that achieve the same outcome, but with fewer faults overall in the final product, particularly with respect to microelectronics. Well, the point is this, that nanoimprint technology is not limited to microelectronics, and novel applications are being discovered. Furthermore, with respect to optical lithography specifically, the entire process is extremely expensive. 30 to 40% of the cost of a microchip is associated specifically with the lithography step. Using optical diffraction means the feature size is physically limited by the wavelength of the light being used. Improvements have been made, but it's still a physical limitation. Patterning can only take place on photosensitive resists. This is a big limitation on the possible materials that can be used, and again contributes to the point made before. These resists add considerably to the cost of the operation. And lastly, the technology cannot easily be applied to non-planar surfaces. It simply means that there is a limitation to the applications of this technology. So we start now by introducing nanoimprint lithography, not as a replacement, but as an alternative to lithography, as an alternative lithography technique. It is relatively lower cost, easy to implement, and can be used on a variety of polymers, as well as other materials such as sol gel films or metallic films. So the talk today will begin with an initial introduction to the first classic NIL, followed by a brief discussion of its issues. I'll then introduce two alternatives to this method and discuss their strengths and weaknesses. We'll then move on briefly to discuss three slightly different approaches, and afterward I'd like to speak generally about the overall difficulties of this technology. Lastly, we'll discuss the possibilities for large-scale fabrication, as well as some of the interesting applications of NIL. So here I introduce you to the basic idea and concepts of nanoimprint lithography. You have a mold or stamp, which is typically silicon, glass, quartz, or even another polymer, and you push the mold into a thermoplastic polymer. The whole apparatus exists in an oven, so the temperature can range between 125 to 200 degrees centigrade. The key point is that the thermoplastic is an amorphous material. It's highly viscous and can be called what we would say a frozen liquid. As the temperature rises, it passes a point called the glass transition temperature for the polymer, which is simply a temperature in which a phase change is observed, meaning the polymer moves from a solid to a molten state. So the template or stamp is pressed into the polymer under quite high pressures, and the polymer replicates the pattern surface, or rather, there's a negative replica of the pattern, so the topography is inverted. The temperature cools below the glass transition temperature, which may take anywhere from minutes to hours, and the pattern is removed. If access to the initial substrate is required, reactive ion etching can remove the residual polymer from those wells with a further processing step. So it's quite simple. You take a rigid mold, push it against a soft polymer, allow a shape conformation, and remove the mold. Okay? Awesome, we've got that. Now I just want to take a moment to quickly highlight some of the difficulties associated with the technology, but specifically with this process before I move on. The primary issues are as follows. There usually exists a difference between the thermal expansion coefficient of the stamp and the polymer substrate. This means that each expands and contracts at different rates as the temperature varies, meaning as cooling occurs, the polymer will not conform strictly to the same dimensions that you printed. This seems to be an inevitable result of temperature-based nanoimprinting. Secondly, there exists a difference of pressure shrinkage coefficients between them also, which has a similar and compounding effect. With these two factors mentioned, however, it must be said that there is an extremely high fidelity associated with these techniques. In fact, back in 1998, 25 nanometer imprints were demonstrated, and in 2004, 5 nanometer prints had been shown. So an interesting advancement I'd like to mention on this technique eliminates the need for an oven and also dramatically increases the processing time of the chips. This technique is known as rapid flash patterning. So essentially, the basic principles are the same. However, a high intensity infrared lamp is employed to perform the heating step. With a 10 kilowatt IR lamp, heating can be achieved in 10 seconds. The polymer surface can reach temperatures of over 250 degrees centigrade. So we have a substrate and the polymer layer as well as the mold. Imprinting occurs while IR exposure is happening, deformation occurs, and the stamp is removed. This technique works to vastly improve processing time. However, it still does not address the issues we just previously mentioned relating to the thermal and pressure coefficients. These issues are still apparent with rapid flash patterning. So now I'll introduce you to another technique which tries to limit these issues. So here is the technique called step and flash lithography, which is actually the technology we were introduced to briefly in the week 2 lectures. So effectively all of the initial components of the operation are identical. There's a stamp and a substrate, there may or may not be a polymer layer, and what happens is a liquid resist is deposited onto the substrate. You see, having the resist liquid at room temperature means the issues relating to the thermal coefficient don't apply. Furthermore, high pressures are not needed, so the pressure coefficient plays less of a role also. So we presently eliminated 2 of the major concerns that we have been introduced to. There are other concerns, but I'll come to them soon enough. So the substrate and mold are pressed together, and here is the critical feature of step and flash. A UV light causes polymerization of the liquid resist, so there's a phase change, and this is how the features are retained after the mold is removed. Okay, so fair enough. Pretty interesting. Let me discuss a few associated difficulties. Firstly, the resist. It must necessarily be a liquid at room temperature, also being UV cross-linkable. This is a significant material restriction. Secondly, we must fabricate UV transparent molds to allow the process to take place. Also, interestingly enough, we still encounter a volume shrinkage due to the phase change of the liquid resist. Okay, let's step back and think about this. The issue of concern here is the volume variability of the polymer we wish to shape. We took 2 approaches. The classic heating option intrinsically leads to a volume change, as the vibrations between each polymer molecules varies upon heating and cooling. The second polymerization option intrinsically leads to a volume decrease due to the cross-linking of the polymers as they physically move closer and occupy less space. I'm not actually certain that these difficulties are escapable, but despite this, they have been used to very effectively, again, produce high fidelity products. I want to now briefly mention 3 other approaches to nanoimprint technologies: solvent vapor-assisted NIL, room temperature NIL, and laser-assisted direct imprint. So solvent vapor-assisted NIL involves saturating the polymer with solvent vapor by keeping the substrate in a tank containing the solvent. Let's look at the diagram. The solvent penetrates the polymer and surrounds the individual polymer molecules. For example, it could be toluene with a polystyrene polymer. This has a number of effects. The film will increase in size with more molecules attempting to fill the same space. It also effectively lowers the glass transition temperature as the film viscosity decreases, so the print can be performed at lower pressures. Problems may arise though, as after printing, the solvent can escape, which often will lead to structural damage. Interesting option, let's move on. The second example, room temperature printing. You effectively take the original substrate and apply very, very high pressures. You're able to actually enable a plastic deformation. You can imagine, as a result of a technique like this, the final molds have lower fidelity than other techniques. Another issue is a lot of stress is imparted into these structures, which is actually periodically distributed, and they are prone to release. Also, the molds required must be exceptionally hard to resist breaking at high pressures. Lastly, laser-assisted directed imprint or LADI technique involves taking an excimer laser and directly creating a molten silicon phase with the substrate surface, and we imprint the mold directly. The work has been demonstrated, though I actually haven't seen any results from this type of method. Okay, with this slide I'd like to discuss some of the issues and expenses relating to these NIL methods. They definitely exist. The template made of silicon oxide, carbide, nitride is typically fabricated using electron beam lithography. So in a sense, this optical lithography is not completely disposed of with these methods, and as a result, this is the most expensive procedure during manufacture. Often secondary masks may be made using the original with some cheaper high molecular weight polymer, as the longevity of these masks is of very high importance. Another relevant issue is the fill factor, which relates to the amount of polymer, usually a liquid in this case, available to fill the required template. It varies over the surface of the stamp and has multiple consequences. If too much polymer is used, more time is required for it to squeeze out the bottom. If too little, the required topology isn't achieved. But more importantly, as the fill factor varies, the sinking rate of the stamp also varies, leading to artifacts in the product. Two methods have been employed for these difficulties. In some instances, a dummy cavity or a protrusion is added to ensure the average fill factor remains constant. Secondly, with liquid polymers, an inkjet application can control the spatially required volume. Let's take a moment for me to catch up with the diagram. Okay, just quickly, overlay is difficult control. This relates to holding the substrate accurately in the same position and also to performing multiple patterns on the same area. Pressure applied during the press can cause deformations in the substrate. Pressure points are made on the substrate to account for these deformations and correct the features. Pretty interesting. But now, let's get to the biggest issue, defects. The one big drawback of the NIL technique is defect percentage. Typically, defects are around the 1% mark, but for industrial applications, it needs to be 0.01%. That's 2 orders of magnitude difference. Defects occur for a host of reasons. I'll mention just a few. Hydrodynamic stresses are intrinsic to the pressing process. If you follow the diagram, viscoplastic deformations moving along these tracks cause stress in each protrusion. Under certain circumstances, these stresses can release, changing the pattern geography, losing structural height, hampering functionality. Foreign materials also pose a threat. These operations are typically conducted in high-level cleaning labs to account for this. Another large factor is adhesion of the template to the material. Adhesion of the stamp to the polymer is typical, and usually large pressures are required to remove the template. The resulting chance of defects or damage is quite high. An anti-adhesion factor, which is simply a liquid with a very low surface tension, is added to the mask, which dramatically increases the quality. This ultimately results in reduced pattern damage, reduced stamp damage, increasing stamp life, and is a key requirement for cost-effective printing. Finally, we get to fabrication and applications. So on fabrication, a key advantage of the NIL technology is that it is not restricted to rigid substrates, meaning flexible polymers are completely available for use. Fabrication has been demonstrated in various ways on the large scale. For example, one large-scale application approach uses a rolling stamp to imprint on a planar surface. Methods like this have been used to print, for example, the polarization layer for large screens TVs. Interestingly, the polarization possible with these techniques has been demonstrated to be 10 times more effective than chemical polarization. Other applications being researched involve printing colored materials with no use of pigments. This is achieved by matching the grid spacing to the wavelength of a desired color. It was inspired by an observation of this phenomena in butterfly wings and represents a form of material fabrication known as biomimicry. Another example of biomimicry involves analyzing surface topography of roses and lilies, replicating the water adhesion properties of each. Further work is looking at producing shark skin-like material, which actually has antifungal properties related to its physical topography. Very interesting. And lastly, I'd like to mention the most immediate application of NIL as it stands today, which is aiding the transition of the hard disk industry to more effective bit pattern media. Here's an incredibly quick summary. A homogeneous magnetic media is applied to a surface. Its surface is divided, like in a grid, into bits, each having directionality that is readable and writable. Now, as the bits get smaller and closer, they are no longer independent of each other and unusable for media storage. However, three-dimensional hollow pits containing bit pattern material, as is possible with NIL, do not interact with each other, so closer packing is possible. Moreover, hard disks are tolerant to defects. You merely identify the defective bits and don't use them. It's a very viable application. So what I did today is I discussed why research into nanoimprint technology is relevant. I introduced the first classic NIL, followed by a discussion of its issues. I then introduced two alternatives, rapid flash patterning and step and flash patterning, and discussed their strengths and weaknesses. I then moved to mentioning the technologies of solvent vapor-assisted NIL, room temperature NIL, and laser-assisted direct imprint. We discussed the difficulties of this technology, and lastly, moved on to large-scale fabrication, as well as the interesting applications of NIL, particularly relating to bit pattern media. I hope the tutorial has been enlightening, and thank you for your time.